Hello. So today what we're going to do is we're going to talk about how to interpret expressions, right? Especially ones that involve word problems. So don't be scared. We're going to talk through them together, right? I know it's a word problem, but it'll be all right. So first up, let's kind of review some vocabulary that hopefully you've seen sometime in the past. So first up, we've got a variable, right? A variable is just a letter or a symbol that represents a number we don't know, right? So it might be a number that we're looking for. It might be a number that we have to take from the problem and plug in for something, right? But that's all it is. It's just your x's or your y's or something like that. A coefficient is the number in front of a variable, right? So for example, if I had something like 3x, the 3 is the coefficient. The x is the number we don't know, right? That's our variable there, right? So we got a little different piece on each. The terms are I like to think of them as the chunks of the expression, right? They're made up of variables and numbers, right? You don't have to have numbers with it. It could just be variables. It could just be variables and no numbers, right? Either way. Or you could have a little bit of both, but they're the chunks of the expression, right? The operators are the things that we do, right? So if you think about what we normally do with numbers, right? We can add, we can subtract, we can multiply, and we can divide, right? Those are our basic operators that we're going to be using, right? So as you've probably seen in the past, the multiplication can also look like a dot, right? The division can also look like a slash, right? And those are things to also look out for. Those would count as operators, right? The constant, however, is a little bit different than all of these, right? It's just kind of base level. It's a number by itself, right? There's no variable to it, right? So whereas above there where we wrote 3x, right? The 3 in that case is a coefficient. If we got rid of the x and we just had the number 3, right, all by itself, no variable in sight, then that's just a constant. The reason we call it that is because 3x changes depending on what the x is, right? That whole chunk of stuff will be different depending on if x is like 2 or if x is 7 or what have you. The constant, say my constant in a problem was 7. It doesn't matter what x is, that 7 will stay 7. It stays constant. All right, we've also got this thing called an expression, right? This is when we have a collection of terms connected by either a plus or a minus, right? So whenever you've got those plus or minus kind of breaking up the chunks, then that's an expression, right? The way that it turns into an equation, which is, not on here, but we'll talk about at some point, an equation has to have an equal sign in it. An expression, notably, does not. Evaluating, right, just means that we're replacing a variable with a number and solving it out. That's one of the things that we did in the last lesson is we plugged in a number for the variable and we kind of simplified it using our order of operations. All right, so what we're going to do here is we're going to try identify the different parts of this expression. So we got 4x plus 7y minus 13. All right, so first up are the variables. If I'm thinking about what the variables are, right, they are just the numbers, the letters that represent numbers we don't know. All right, so if I'm looking in there, my variables would be x and y. Right? Next up are coefficients. Those are the numbers that are in front of variables. So in this case, there's a 4 in front of that x. Whoops. So the 4 would be a coefficient. There's also a 7 in front of the y. So the 7 would be a coefficient. The 13 is not a coefficient, right, because it does not have a variable right next to it. Right? Then we've got operators, right? And remember that the operators are the things that we do, right? So we've got a plus sign, we've got a minus sign, and then it's a little bit tricky, right? It's one of those invisible things, like you have invisible ones every now and then. There is also multiplication going on in there, right? So let's talk about why. I'm going to kind of zoom in on that for a minute. When I've got something like 4x, what's really going on there is that it's 4 times x, and that 7y is 7 times y, right? So it's kind of like having a little hidden operator in there, right? That's what a coefficient is doing. It's telling you, all right, 4 times this x number, whatever the x happens to be, right? I'm going to be honest, if you didn't write down multiplication as one of your operators, I'd still be fine with that, right? It doesn't show it, right? And sometimes it's a little hard to remember that it is there, right? But either way is fine. Right? After that, we've got the terms, right? And again, the terms are the big chunky pieces of this, right? So 4x is a chunk, right? And then it's got an operator. 7y is another chunk, and then there's another operator. 13 is its own chunk, right? So whenever you have things separated by operators, specifically the ones that are actually written out there, right, those invisible little multiplication signs don't really count for this. Whenever you've got like a plus or a minus breaking up the terms, right, that's how you can figure out what the terms are, right? They're separated by plus and minus. Last but not least, the constant is that 13 that's on the end, right? And some people, you could argue that it's negative 13, right, because it does have that minus sign in front of it. You could also just count the minus as an operator and just leave it as 13. Again, either one is kind of fine here. So I'd like you to do, I'm going to leave this one up on there, is pause here, try out this next one, and then see how you do. So hopefully you gave it a go, right? We've got variables. We've got an x and a y, same thing as before. My coefficients, right? And again, this is kind of like what we were just talking about with the 13. You could call them 5 and 9, right? We could also call them -5 and -9 that are kind of attached to those variables. Again, either way is kind of all right. On this, we've got a plus, we've got a minus, and then again, we've got that hidden multiplication going on with those coefficients. Right? We've also got some terms. It's anything that's broken up by operators, right? So again, I could call that regular 5x if I wanted to. I could call this regular 9y if I wanted to. And that 23 is just 23. All right, so again, they're broken up, right? We're taking these different chunks. As for the constant, it's just 23. It's the only thing that is a number without a variable. All right, so what we're going to do is we are going to take a look at some word problems together, right? We're going to talk about what the different pieces are representing, right? We're going to interpret what this is telling us. So Tony's Little League team is selling raffle tickets as a fundraiser to raise money for a trip to see a Major League Baseball game. Cost of participating in the raffle is given by this expression 5t plus 3. Right? So we're first going to figure out what the heck is the variable and what does it represent. Right? So if you would like to, it's not a bad idea. You can work through that first part of each one of these problems and then figure out what they represent. Right? So the variable in this case is t. So we're going to figure out what t is supposed to mean. The next one down is talking about what the coefficient is, right? And it's that 5 that's in front of the t. And then the constant is that number by itself, the 3. Right? So what we're thinking about, right? Think about the situation. We're participating in a raffle. They're selling raffle tickets, right? So usually the t, right, the variable is going to stand for the number of something. Right? So it's the number of, and then we got to figure out what the something is. So if you're thinking about like participating in a raffle, the number of things that might be changing is how many raffle tickets you're buying, right? You could buy more tickets, you could buy less tickets, right? So t is the number of tickets, right? As far as that 5 goes, right, usually when you have a coefficient on a variable, right, it's the number of something for the variable. So the 5 is kind of like how it's changing, what affects that thing that's changing. So in this case, if it's a number of things that we're buying, right, we're buying tickets, the 5 is actually going to be the price of a ticket. Right, so sometimes we're going to have the coefficient be, the rate of change, right, how fast something is changing. Whenever we're doing something with buying or selling, it's usually the price. And then that 3 at the end is kind of a weird one in this case, right? The 3, I'm just going to tell you, is kind of like the base cost. Right? So if you think about, you go to the carnival or something like that, and you're like trying to, get into Freiburg Fair or something like that, you have to pay at the gate in order to even enter the carnival, right? So what you need to do is you're paying that base cost up front, and then once you're actually in there, then you can participate in the raffle. So that's what it kind of is here. Right? It's that cost that you have to pay before you're even able to buy lottery tickets. All right, let's give another one a shot. Miss KB has a pet tortoise named Toto. When she bought him, she paid $376 for supplies and setup materials. She pays $45 a month for pellets and lettuce to feed him. The cost of owning her tortoise is given by this expression, 376 plus 45M. All right, so again, we're going to work through this one piece at a time. The coefficient is that 45. The constant is 376, right? So remember, the coefficient has the variable next to it. The constant does not. The variable is M. It's the only letter that's in there. And then later on, we're going to get to talking about why she used addition in her expression. All right, so let's think about what we've got here. The coefficient is 45. So if I'm looking back in the problem, right, it says that she pays $45 a month for pellets and lettuce to feed him, right? So it sounds like that's going to food, right? So 45 is the food cost, right? And specifically, we can get a little bit more particular. It's $45 a month, right? So it's the food cost each month, right? Sure would be cool if it was only $45 once and then like, oh, cool, that's it, right? But it's $45 each and every month to keep that up. The 376, that's what she paid for supplies and setup materials, right? So that was kind of the money that she had to spend right out the gate. So we can kind of think of that as our initial cost, right? If you also wanted to call it the base cost, kind of like we did in the last one, that's kind of the same thing, right? It's the money that you had to pay right at the start to even get underway with things, right? The M, let's think about what's going on in this problem, right? She paid $45 a month, right? And I'm noticing that next to the 45, there's an M, right? So that M might be talking about how many months go by, right? So just like on the last one, I was talking about how the variable is usually the number of something, right? In this case, it's the number of months, right? So whenever you're talking about something happening over time, right, like we're talking about the cost over time, the variable is oftentimes going to be that unit of time that you're using, right? Last but not least, why the heck did we use addition here, right? So, to kind of answer this, think about like, well, why didn't we use subtraction, right? Why didn't we multiply, right? We didn't use subtraction because we're not, taking away the cost from the initial cost, right? We're adding on money, right? That's really what's going on. We are doing this to combine to get a total cost. Right? It's like, why do you add things when you go to Hannaford, right? You're adding things on to your bill, and then you have to pay them all at the end. Right? So, next up, you owe your dad $300 for Nintendo Switch. You're paying off the debt by $15 per week by running errands on the weekends. This expression represents your debt. Yikes. Right? So the coefficient, what does it represent? The coefficient is that number in front of the variable, the 15. The variable is W, and the constant is that negative 300. All right, so first things first, 15. What's that coefficient representing? So I'm going to look back in the problem. I'm paying off the debt by $15 per week, right? So that's the the weekly payment. Right? That's how much I'm trying to give back every week to pay off that debt. Right? After that, we've got the W, right? And again, it's the variable. We're talking about the number of something, right? And then we got to, again, look back in the problem, right? You're paying off the debt by $15 per week by running errands on the weekends. This expression represents it. So, again, we're talking about this thing that's happening over time, right? So that time unit is probably what our variable represents. In this case, that's going to be, weeks, right? There's another little trick that you can use, right? You notice that where we have the 15, right, it's right next to the variable in our expression, right? $15 per week. The 15 is next to the W. Whenever you see this word per, right, and if that is next to the variable, The next thing that it talks about is oftentimes going to be what your variable represents. So $15 per week, right? That means that that's what that W is, right? Per week, 15W. Right? So I can kind of help you figure that out as well. The negative $300 is kind of like what we started with, right? So again, it's our initial, amount. I mean, again, you could call it a base cost, you could call it an initial cost. It's the initial amount of money owed in this case, if you wanted to get really particular. Right? But that's really all it is. Right? So what I'd like you to do is we've done a couple of these together. I want you to try out this next one, right? You're 12 miles from home on a trip to see your crazy Aunt Margaret. You're traveling 45 miles per hour. You're bored, and you write this expression to model how far you've traveled over time. Right, so figure out the coefficient, the constant, the variable, what they stand for, and then try that last one for what the operator is. So hopefully you gave it a show, right? What's the coefficient? It's that 45. The constant is 12. The variable is h. And the operator is a plus sign, right? So looking back at the problem, we're traveling 45 miles per hour, right? So 45 is the miles traveled each hour, right? We are already 12 miles from home, right? So we probably weren't going 45 miles an hour the whole way, right? You don't tear out of the driveway at 45, hopefully, right? So 12 was our starting distance. Right, so we were already 12 miles from home before we had the brilliant idea to come up with this expression. The h, again, the variable is the number of something. And in this case, the something is hours, right? So again, I'm looking at the expression. It's 45 with the h next to it. I'm looking back in the problem, 45 miles per hour, right? So h is the number of hours. Last but not least, why would we be adding, right? The reason that we'd be adding is because we want a total distance, right? And if you're trying to figure out how far you've gone, you know, if you went 1 mile and then you go 2 more miles, you just add them together, right? You wouldn't multiply, you wouldn't divide them for sure, right? So you're continuing to add on to that initial bit, right? So what I'm actually going to do, because I don't want this video to go on for forever, is I'm going to leave these ones up to you. When I upload these to our Google Classroom folder, I'm going to have these all filled in. Oh, actually, hold on. I take that back. Right? These ones are a little bit different. Let's kind of run through them real quick. A local bakery sells cupcakes and cake pops. Cake pops are $2.75 a piece, and cupcakes are $3.90 a piece. Based on how many they sell, this expression can be used to calculate their income. 2.75C plus 3.90p. Right? So what are the terms? Right? So the terms, again, are these big chunky pieces. So 275C and 390p. Right? So we got to then look back through the problem and think about, like, all right, there's two variables. Right? One represents one thing and one represents the other. So in this case, the 275, right, back in the problem was talking about the cake pops. Cake pops are $2.75 a piece, right? So it would stand to reason that that $2.75 is the money from cake pops, right? Same kind of logic will get us to this other piece, right? The cupcakes are $3.90 a piece, right? So that $3.90 is the money from the cupcakes. Right? So, last but not least, for this one at least, right, is that what is our operator? It's that plus sign. Why did we choose it? Because we're combining the profits to get a total. Right, so we're trying to figure out the total amount of money we earned. The way that you add to get the total is you have to add those numbers together. All right. The last one. Right. Peter and John helping take care of the environment by planting trees. Peter plants a maple tree. John plants an oak tree. Each month, they both return to their trees to see how much they've grown. They each create an expression to model that growth of their trees over time. Right? So what do the terms represent in each expression in the context of growing trees? Right, so we're going to kind of group these together. I'm noticing that I have some constants. I have a 6 and I have an 8. Right? The 6 and the 8 are probably like they're like a starting point, right? That's what the constants have always been, is it's like where we started, right? So it's the initial height of the trees. Right? The other terms that we have are this 0.6x and this 0.4x, right? And as we've been seeing, right, that piece where, you've got a coefficient and a variable, that's when it's talking about like how much things are changing, right? So we could call this the height added each month. Right? Because the trees are growing, we're adding, and then we're adding on that little bit every single month. Right? We also have to figure out what the variable is, right? So the variable is x, and what does it represent? That's a good question. So think about, that height added each month piece, right? The maple tree seems to be growing 0.6 feet per month. The what did John plant? John planted an oak tree, right? His seemed to grow by 0.4 feet each month, right? And it's that each month part that kind of clues us in. X is the number of months. And so again, variable in this case, just like on some of the other ones, represents the unit of time that we're talking about. Last but not least, which tree will be the taller tree as time passes? Explain your reasoning, right? So let's think about it. Peter's started at 6 feet and is growing by 0.6 feet per month. John's started at 8 feet but is growing 0.4 feet per month. So if I'm looking at this, right, Peter's tree started out a little bit smaller but is growing faster. John's tree started out a little bigger but isn't growing quite as fast, right? So I'm going to say that Peter's tree will win because it's growing faster. Right, so we're really looking at that rate of change to figure out what's going on here, right? It's this 0.6 that really put Peter's tree ahead of John's tree, which is only growing 0.4 every month. All right, so I'm going to peace out for now. If you have any questions about this stuff, please ask them. This is not a super easy thing to do. And the best way to do them, unfortunately, is just to kind of power through and keep working on them. Right, so please ask about questions if you have them when I see you next time, and I will peace out for now. Bye.